In this section, we're going to talk about what happens when we have an acceleration vector that is not aligned in the same direction or along the same axis as our velocity vector. So we started this semester looking at straight line motion, either along the x or the y axis. And then even when we went to projectile motion, we separated out those x and y motions. So we're thinking about velocity and acceleration along the y axis or the x axis. So now we want to think about what happens when I have this additional component of acceleration. So let's take a look at what I mean. So if we have I'm going to say this is some velocity vector. So I have some object here I'm representing with my particle. And I'm going to say there's an acceleration at this particular point acting on the particle, and that acceleration is directed at some angle theta relative to my velocity vector, right? So this is a thing that is new that we're introducing. So if I have this situation, I want to think about that acceleration, kind of just like we did with projectile motion, we separated into X and Y motions. I want to think about this acceleration in the context of that velocity, how it's acting relative to the velocity. So I want to think about a component that is parallel to my velocity, and then a component that is perpendicular to my velocity. So I'm going to take that acceleration and we're going to think about the effects of the parallel component and the perpendicular component. So if we start with a parallel component and I kind of ignore everything else, right? Just think about that velocity and A parallel. The A parallel is in the same direction of the velocity. So this goes back to stuff we've already been doing. So if I have an acceleration directed in the same direction of my velocity, then we know that our object is speeding up. So an A parallel, so an A that is directed along or parallel to the velocity vector, this is going to result in a change in speed. So if the direction is the same direction as velocity, if they're both going in the positive direction, they're both going to speed up, or both going the negative direction, they're going to speed up. And if the acceleration and velocity are in opposite directions, but along that same axis, right, so parallel to each other, then our object can be slowing down. So acceleration in the same direction or parallel to velocity causes a change in speed. If I look at the other component, so this is the new piece for us. I'm calling this A perpendicular. So A perpendicular is that component of the acceleration that is perpendicular to our velocity vector. So this does not have any component that is affecting the magnitude of my velocity vector, right? It's not going to increase that magnitude of the velocity vector or decrease. So it is not going to change the speed. What that A perpendicular is going to do is change the direction. So if I have a component of acceleration that is perpendicular to my velocity vector, this is going to cause a change in direction. No change in speed, but it is going to cause a change in direction. So similar to the fact that the perpendicular is not going to cause a change in speed, the parallel component is not going to cause a change in direction, right? These two things are acting independently in that sense. The parallel piece is going to change speed, the perpendicular piece is going to change direction. So if we take a look at, I've got a couple of different scenarios here, 3 different scenarios here. We just want to quickly run through what each of them means or what's going on in each case by just looking at those velocity and acceleration vectors. So in each case, I'm going to just identify a theta. So I'm going to throw these guys in here. So there's theta. And so in the first case, we have theta is less than 90 degrees. Here we have theta is greater than 90. And in the last one, we've got theta is equal to 90. So theta greater than 90 and theta equal to 90. Okay, so in each case, we just have a car and we're looking at a top view. So you can see the car is moving in a curve like up to the right. The velocity vector is at tangent at that point. So that's telling me at that particular point, the magnitude of that vector is telling me the speed. And the direction of the arrow is telling me the direction that we're moving. So that green is our velocity vector, A is our acceleration vector. So I would just want to know what's going to happen. If I think about the car as it's moving forward, what's happening, how can I describe its motion? And to do that, we can split our acceleration vector into components. So here's my A perpendicular. And then here I'm going to have an A parallel. So the thing we just want to notice here, right, that A perpendicular, this is the piece that's going to cause us to turn. So that's causing us to turn to the right. And then this A parallel, this is parallel to my velocity vector. So that's going to be the part that's impacting the speed. Since it's in the same direction as my velocity, we know that we are speeding up. So in this case, we're going to speed up. If we look at the second one, same thing. Here's my A perpendicular. That's the piece that's going to cause the change in direction, the turning to the right. And then the component, the A parallel in this one, is parallel to that velocity vector, but it's in the opposite direction. And so we know if acceleration and velocity are opposite direction, then that means our object is slowing down. So this one is going to slow down. And then in the third one, we have theta is 90 degrees. And so if theta is 90 degrees, this is my A perpendicular. There is no A parallel, right? There's no component of that acceleration that is parallel to that velocity vector. So I'm not going to have a change in speed. I'm only going to change direction. So this one is going to be constant speed. So by just looking at the relative positioning of the acceleration and velocity vectors relative to each other, we should be able to describe that impending motion, right? What's coming next? Is the direction going to change? And if so, which direction is the object going to move in? And then also, is it going to be speeding up or slowing down? So theta less than 90 means we have a component of acceleration in the same direction as velocity. Theta greater than 90, we're going to have a parallel component of that acceleration that is opposite direction of velocity. And for theta equals 90, we're going to be moving in constant speed. So no component of that acceleration that is parallel to our velocity.